Hello, my name is Ian Lumsden. I'm a PhD student at the University of Tennessee, Knoxville, and I'll be presenting my poster titled Enabling Transparent, High-Throughput Data Movement for Scientific Workflows on HPC Systems. Scientific workflows move data, often in the form of files, between their components using the producer-consumer paradigm. Currently, there are two main approaches to this paradigm in workflows, the sequential approach and the in-situ approach. However, these approaches have several drawbacks. First, the sequential approach is unable to provide consumer synchronization at the per-file level. This requires producers and consumers to run sequentially to prevent consumer computation from running before data is available. Second, the sequential approach suffers from poor temporal locality due to sequential execution and poor spatial locality due to needing to save files to a shared storage location such as Lustre. Third, the sequential approach has low performance for file metadata operations due to its use of shared storage. The in-situ approach mitigates the disadvantages of the sequential approach, but in the process, it introduces disadvantages of its own. The in-situ approach requires substantial changes to workflow code, which discourages workflow developers from adopting in-situ implementations. To overcome these challenges, we design and implement the Dynamic and Asynchronous Data Streamliner, or DYAD, to provide high-throughput data movement with little to no changes to the code of a workflow. To do this, our tool implements the UBEAK approach. UBEAK acts as a middle ground between the sequential and in-situ approaches. Like the sequential approach, data is staged in the file system before being moved. However, like the in-situ approach, producers and consumers store data in a node local location. Additionally, producers and consumers can run in parallel, with consumer synchronization occurring per file transfer. There are two main benefits to implementing the UBEAK approach in DYAD. First, it allows us to create a tool that is easy to use and integrate. DYAD provides three interfaces to users, all of which intercept the file I/O interfaces of POSIX or the desired programming language. These easy-to-use and integrate interfaces allow DYAD-enabled workflows to be easily and quickly constructed. Additionally, DYAD's dependence on widely used POSIX I/O allows workloads to be portable between systems. The other benefit to implementing UBEAK and DYAD is performance. By providing per-file transfer synchronization of consumers, DYAD enables producers and consumers to run in parallel. Additionally, DYAD's use of node local file storage enables faster I/O and metadata operations compared to the sequential approach, which uses parallel file systems like Lustre. DYAD is implemented as a disaggregated server-client design. It is built on top of the Flux resource manager and the UCX networking framework. The DYAD server transfers data from producers to consumers. It is designed as a Flux broker module. This allows the server to be distributed across the same nodes of the workflow without using large amounts of resources. The DYAD clients are libraries implementing the three previously mentioned interfaces. At runtime, the DYAD clients linked to producers will save metadata for produced files to the Flux key value store. The DYAD clients linked to consumers will then read the metadata for requested files. If a requested file is on a different node, the consumer's client will contact the server using Flux's remote procedure call component to initiate a UCX-based transfer of the file. To compare DYAD's performance to the sequential approach for data movement, we consider two benchmarks. In the top figure, we run a synthetic benchmark that spawns several pairs of producers and consumers and transfers 64 fixed-size files within each pair. Between each file transfer, we perform a sleep of 1 second to emulate computation. In this figure, we see that DYAD outperforms the sequential parallel file system-based approach at all scales. In the bottom figure, we run a custom benchmark which emulates data movement in a molecular dynamics, or MD, simulation. Like the synthetic benchmark, we spawn multiple producer-consumer pairs and transfer 64 fixed-size files within each pair. However, in this benchmark, computation is represented by on-the-fly generation of synthetic data. The data in this benchmark is indicative of MD frames, or snapshots of molecular systems containing a fixed number of atoms. In this figure, we see that DYAD is up to 6 times faster than the sequential approach for small and mid-scale runs of our benchmark. However, for larger file sizes, we see that DYAD performs similarly to the sequential approach, suggesting that further optimizations are needed to ensure efficient scaling for large files. In conclusion, we have designed and implemented DYAD, a middleware for efficient and easy-to-use data file sharing in scientific workflows. Through our evaluation, we show that DYAD can speed up small and mid-scale workflows by up to 6 times compared to the sequential approach. In the future, we will examine DYAD's performance at larger scales and for a broader set of applications, including data parallel deep learning and advanced molecular modeling workflows. Thank you for listening to this presentation. If you're interested in this work or have any questions, please come see me during the poster session at the conference.